In this lesson, we're going to derive the formula for areas in polar coordinates. The general setup is suppose we have some polar curve given by r is some function of theta, and we want to find the area bounded by this polar curve on some interval theta in between a and b. So the picture here shows some polar curve r equals f of theta, and we want to find the area in between the angles theta equals a and theta equals b. So this yellow area swept out by the polar curve in between theta equals a and theta equals b. To do this, let's recall the method that we used for finding areas in ordinary xy Cartesian coordinates. So remember, the idea here is that if you had a function y equals f of x, you took your interval a to b, so here it was x in between a and b, you took your interval a to b and you divided it up into these rectangles. So you divided it up into n rectangles, and you said, well, the width of each rectangle is what we call delta x, so that's going to be b minus a over n, the length of your interval, and then the height of each rectangle is going to be f of x sub I star, where x sub I star is equal to some point in the ith subinterval. So f of x, that's the height of your function. X sub I might be the midpoint, it might be the left endpoint, it might be the right endpoint. So f of x sub I star is the height of the function at some point in the ith rectangle. And so then we say, well, what's the area of a rectangle? Well, area of a rectangle is the height of the rectangle times the base of the rectangle. So the area of each one of these small rectangles is just the height, which we said is this f of x sub I star, times the base, or the width, which is delta x. So that's the area of each one of them. We want to add up all of the rectangles, so we get the sum from I equals 1 to n. We want the total area under the curve, so we add up the areas of the rectangles. And finally, we take the limit as n goes to infinity, so we let the number of rectangles go to infinity. So remember, we called this a Riemann sum, and we said this is how we defined our definite integral. So the area under the curve is the limit as n goes to infinity, sum from I equals 1 to n, f of x sub I star delta x, where again x sub I star is some point in the ith rectangle, and so we said this is how we define or construct our definite integral, integral a to b f of x dx. So integral a to b f of x dx, that represents the area under the curve, and it was constructed as a limit of Riemann sums. So now let's do a similar idea for the area bounded by a polar curve. So again, here's our setup. So we have some polar curve r equals f of theta in between theta equals a and theta equals b, and I want to figure out what the area of this region is equal to. So we're going to use a similar idea. Instead of dividing our section up into rectangles, we're actually going to divide it into wedges. So the first thing we're going to need is just a formula that you should recall from geometry, which states that if we have a sector or a wedge of a circle, so if we have a circle with radius r and we have a wedge with internal angle theta, then the area of that wedge is 1/2 r squared theta. So again, instead of dividing into our region up into rectangles, we're going to divide this region up into wedges or sectors, so we need to know what the area of each wedge is. We recall again from ordinary geometry that if theta is that central angle, then the area is 1/2 r squared theta. So now we, as I said, take the region that we're trying to find the area of, we divide it up into all of these wedges. Just like before, I'm going to let theta sub I star be an angle in the ith subinterval, and then the idea is that in this highlighted wedge here, so the area of this highlighted wedge is just my 1/2, r is my f of theta sub I star, so r squared, and then the angle, just like before, the base was my delta x, the angle is now this delta theta. So again, remember from the previous slide, if you have a wedge, the area of that wedge is 1/2 r squared theta. So we're using that formula, area is 1/2 r squared theta, and in a wedge, our r is the f of theta sub I star, and our angle is that delta theta that we get by dividing our region up into n subintervals. So we're using our formula from geometry, again, just like we did with rectangles, and finding the area of each of these small wedges formed by the subintervals. And then again, just like before, we're going to form our Riemann sum. So our area, we want to add up the areas of the wedges. So we're going to get limit n goes to infinity, sum I equals 1 to n. Again, remember from the previous slide, the area of each wedge is just 1/2 f of theta sub I squared delta theta. So plugging that in, I'm getting 1/2 f of theta sub I star squared delta theta. Taking the limit as n goes to infinity, this gives us our Riemann sum. So we get an integral formula for the area. So the area bounded by a polar curve in between theta equals a and theta equals b is exactly this formula, 1/2 quantity f of theta squared d theta, or 1/2 r squared d theta. So the important point at this point is to remember this formula, be able to use this formula in some examples, which we'll do next, and have a general idea of how we obtain the formula, which is just like we do in the ordinary case. We divide our region up into subintervals and then use geometry to find the area of each subinterval. Finally, we take a limit as n goes to infinity, which gives us our Riemann sum, which gives us our integral.